Welcome, dear participants, to our online series Medium Voltage Technology Essentials. My name is Pedro Gomez. I work as a Product Lifecycle Manager for air-insulated medium voltage switchgears, and today I am here with my colleague Miriam Johansson, who works as a Product Lifecycle Manager for gas-insulated switchgears.
I would like to share my personal motivation for creating this training with you. I've been working for Siemens AG since 2017. As a mechanical engineer, I switched from the agricultural and construction equipment industry to medium voltage technology, with which I had hardly any contact at that time. I would have appreciated a compressed basic training when I started. So, I'm more than happy to welcome you to this series.
The Medium Voltage Technology Essentials series comprises 7 informative videos, organized into 3 comprehensive blocks. My colleagues and I will guide you through the topics of power supply, components of a medium voltage switchgear, design criteria, construction of a switchgear, our medium voltage portfolio, as well as the current topics of digitalization and sustainability.
Should you have any questions during our series, please do not hesitate to use the Q&A feature located in the upper right corner of this platform. We will ensure that each question receives a detailed response via mail after the event. If you are in full screen mode and cannot see the Q&A field for questions or the chat box, simply press the escape key to exit full screen mode. Now, enjoy your journey on improving your knowledge of medium voltage technology.
And to conclude with the words of the Chinese philosopher Laozi, learning is like rowing against the current. If you stop, you drift back.
Hello everyone, I would like to give you an overview about the components inside a medium voltage switchgear. What are they for? How do they look like? What are they supposed to do in each situation? When should they act, etc., etc. So that you can have a better understanding of how a switchgear works. A switchgear is much like a computer or any other machine where a lot of different components are connected and working together to accomplish a certain purpose. Why do we need a switchgear at all in the first place? Well, we need them to switch energy on and off. You can memorize that. That is the function of a switchgear. Switch on, switch off. That's it. That's as simple as that. We could as well say that we build airplanes because we want to fly. That doesn't say anything about the parts of the plane or how it flies, nor about how the many different parts and systems that have a contribution to achieve the final target of flying. And that is pretty much the same thing with the switchgear. The good thing, though, is it's a lot easier to understand how the components of a switchgear work than to understand those of an airplane. So, therefore, first I will show you where these components are placed in the switchgear, and then I will explain in a simplified way what they are supposed to do. A switchgear consists of some metallic boxes that we usually call panels, connected together that share a common busbar. Just like your fuse box at home, there is a busbar and a voltage, which is a common connector to all those boxes. At home, we don't have boxes or panel, we have little switches called miniature circuit breakers that are able to cut or re-establish the power when your finger slides them up or down. The main difference between that and the medium voltage switchgear is that we usually have 3 phases instead of just 1 phase, and the power involved may be up to a few thousand times higher than at home. But let's disregard these details for now, as you will learn more about that in other units. A switchgear has an incomer panel, or several, that are connected to the network where the power is available. This is the entry of the energy to the switchgear. The other panels are used to connect consumers, like motors, transformers, etc., to the network, exactly like if you would be connecting a light bulb at home. You connect the bulb to the network via the interrupter and via your home switchgear, which is connected to the network. So when one of the protection switches at your home's switchgear switches off, the worst thing that can happen is that there will be a blackout at your apartment if you were unlucky and the main switch opens its contacts. Or, like we say in the electrotechnics world, it tripped. When you switch off the entry, the whole switchgear gets no energy unless there are several entries, or as we usually call them, incomers. On a medium voltage switchgear, the consequences of an unwished trip can mean huge financial losses or, in exceptional cases, even threaten lives. Here we have our switchgear again, and now we will focus on one single unit, which, as said, we call panel. If you open the door and remove the circuit breaker, it looks like this. If we would open its sidewall and look from the left, this is what we would see in most of the panels. This is a cutout picture, as if you would cut an apple and then look from the side. Most of the panels look like this one, but some have some more components. Some are a bit different. If you understand how this one works, though, you will understand 90% of the whole thing. So let's focus on this kind of panel. You can see that there are different compartments in the switchgear. These compartments aren't all the same in all switchgear types. The compartmentalization is a very important characteristic of a switchgear because it allows different degrees of availability. If, for example, the circuit breaker has its own compartment, it can be accessible even when the other compartments are energized. If it doesn't, in order to remove it, for example for maintenance, you will have to switch off the power on the busbar and on the cable compartment before you access it. And when you switch off the busbar, the whole switchgear has no power. If the breaker, however, has its own compartment and is accessible even when the busbar is connected to power, and you can maintain a feeder without switching off all others. The type of compartmentalization of a switchgear is called loss of service continuity category, or shortly LSC. And here you see an example of the most demanding type of LSC, which is LSC2B. That means, in a very simple way, that each of the main functions of the switchgear has its own compartment independent from the others. In a feeder panel, which is a panel connected to something that consumes energy, the current flows from the busbar to the cable compartment. It comes from the busbar, it flows through the breaker, which can open or close its contacts. When the contacts are closed, it flows into the connection compartment into the cables. On this path, you may see that some devices are placed. We will see later which devices are those and what their function are. In an incomer, the current flows the other way around, from the cable compartment to the busbar. But mostly you have the basics done now. The current comes inside the switchgear via one panel, which brings current to the whole switchgear via the busbar, and in each feeder it flows through the breaker into the cables that are connected to a consumer that requires electrical power. Then we have the low voltage compartment, which I usually call the brain of the switchgear. This is where all cables lead to and all sensors are connected to. We will have a more detailed look at this later. And finally, there may be a gas relief chamber where the gases are led into in the event of an arc fault, which causes a big explosion if it's not switched off before. This compartment may be common to the whole switchgear or individual per panel. When it's mounted over all panels, it builds a channel that leads hot smokes and gases to the outside of the switchgear room in case of an explosion. So here we go. Let's have a look inside a typical switchgear and find out about its components. The first component that I would like to highlight is the busbar. As mentioned before, the busbar is one of the main elements because it connects all panels together, and this connection is what makes panels into a switchgear. It acts as a distributor center for the electricity. One panel connects it to the network, as I mentioned before, the so-called incomer, and the other panels, usually called outgoing feeders or simply feeders, connect the devices that need electrical power. It is exactly the same principle as water flowing in a water pipe with many holes or derivations. The water comes inside the pipe and on its way it gets distributed to several openings that goes to different places and consumers. But in the switchgear you can see that we have 3 bars, which are called phases, because the electricity is distributed in packs of 3 and therefore we need 3 bars. So usually when we say busbar, we mean 3 phases at the same time. Busbars are usually made of copper, but also aluminium can be used. In theory, any metal could do the job because it's about transporting electrical current, but copper is usually the best choice for this and therefore the most common. The busbar must be sustained via insulators so that the outside of the switchgear, meaning whatever a person can touch, is always grounded and not dangerous. By the way, this applies to any components that is connected to voltage, also at our homes, computers, mobile phones. Because the busbar carries current, there are two other challenges that it must master. So, as most of the components inside the switchgear, by the way, the heat and the mechanical strengths. In normal operation modus, the busbar gets hot, and this heat must be dissipated so that the temperature inside the switchgear doesn't melt the components, and that the switchgear enclosure can be touched without causing harm to people. In case of a fault, like a short circuit, the busbar undergoes very high forces. The bars themselves behave as very strong magnets attracting each other. On one hand, the busbar must bend, not to break, but on the other hand, it must be kept firmly fixed to be able to perform its function. When you see all these copper bars, you may think it's just copper, but building a busbar is in fact a big technical challenge. Now let's jump into the circuit breaker compartment, also called switching device compartment, since sometimes there are other components than a circuit breaker inside, as we will see later. It's also called often module compartment room. The circuit breaker is the component that opens and closes the power, like the switch you will probably have somewhere in the room where you're sitting that turns the light on and off. But there is a very big difference between this breaker and the light switch you can see on the wall. To switch the light on and off is what it's called opening or operating under normal service. But there is another modus of operation which is much more demanding than that one, which is the disturbed service. In this case, the operation takes place under faulty conditions, which occur rarely due to some failure, like for example when a small animal enters the switchgear. In those situations, huge currents can flow through the switchgear or the voltage can increase tremendously. The current can reach more than 100 times its normal operation value, and the circuit breaker must be able to switch those currents off. A medium voltage circuit breaker is also capable of switching on and off in faulty conditions. Another different thing about the medium voltage circuit breaker is that in air-insulated switchgears they are often withdrawable. That means they can be removed from the voltage contacts while still inside the panel and can be even removed from the panel, for example for maintenance or replacement. One further important thing in this compartment is that it's enclosed by the front door, which is usually the interface to the user. Components like the circuit breaker and the earthing switch are operated through this door. The door must be very sturdy and is usually built to be able to withstand the very worst case situation in the switchgear, the rare event of an explosion caused by an internal arc fault. Even in that event, a switchgear is built to minimize harm to human operator, and this is also one of its most important characteristics, its internal arc fault withstand capability. As mentioned before, sometimes other devices can be used instead of a circuit breaker when the duty is not so demanding or for other specific duties. One of those devices is the disconnector. If it's a simple disconnector, it's also called an insulator because that's all it does. It insulates the next section. As it can't break currents, it can only be inserted or removed when no current is flowing. A disconnector can also be designed to switch operating currents on and off, and in that case it's called switch disconnector. The common thing to both is that they cannot switch fault currents. They are used for creating a so-called safety gap for the safety of the personnel that need to work on equipment downstreams to the switchgear. There are other devices that can be inserted in this compartment. We will return later to circuit breakers in more detail and also talk about some other switching devices and their duties. Let's now talk about other components, the transformers. These devices are placed on the medium voltage path, and their function is to provide information about the values of voltage and current flowing. Therefore, there are two types of transformers, voltage and current transformers. We could also call them sensors, because their function is to send a signal to the low voltage compartment depending on what they detect on the high voltage side. When there is more voltage or current, the signal is higher. When there is less, the signal is smaller. Transformers are usually used for protection or for measurement purposes. They are usually wired to the low voltage box, where a protection device decides what to do when certain circumstances are met. For example, if there is a failure in one motor feeder, the current usually goes up in a certain way that is predictable. If the relay sees, using the information of the transformers, that the current is increasing in that known way, it understands that a failure is occurring and sends a trip signal to the circuit breaker. That way, the current is switched off before the motor gets damaged. This is why it's called protection. It prevents a serious failure from occurring. Sometimes we want to measure how much energy is consumed, and in that case we need measuring transformers with the correct characteristic for doing precise measurement. Because they are connected to the high voltage, transformers are at the same time insulators and are also, like the main busbar, subject to mechanical stress. And of course, we usually need one for each phase, although sometimes there are exceptions. The current flows through the current transformers in series, and that is why the current transformers have two primary connections, for entering and for leaving the device. The voltage transformers have only one connection because they are connected in parallel. And now we come to the final destination of the electrical power after the switchgear, the cables. The cables carry the power and connect the switchgear to the consuming device, which can be a motor, a transformer, a line, a capacitor, etc. Cables are not part of the switchgear and are usually mounted on site. On the way to the cables, an earthing switch might be placed. If energy is flowing, this must be open at all times. The earthing switch is a very important component that connects the phases to earth. It usually connects each of the three phases to the earth and between them. It is used to make sure that an operator in the cable side cannot be exposed to voltage, even if power is turned on accidentally. You might think that we could do this by switching off the power with the circuit breaker. It's partially true, but it's not exactly the same. When you just switch off the circuit breaker, there can be residual capacitive voltages, which could harm an operation with a short but maybe powerful discharge. The earthing switch makes sure that the voltage is really zero and cannot harm anyone. This is why often a padlocking facility is required. When the operator needs to touch the cables, he puts the earthing switch on and he keeps the key on his pocket so that no one can turn it off again. While the earthing switch is connected, nothing can happen to the operator. As you might have guessed, the earthing switch is usually capable of withstanding a short circuit. If an operator is working and the voltage is turned on, the earthing switch will withstand that huge power flow until the upper protection mechanism shuts off the failure, typically within 1 or 3 seconds. The other way around, if the earthing switch is switched on while there is still voltage, a failure occurs and the earthing switch must hold its earthed position until the fault is cleared. This way, the operator is always safe. Of course, there are mechanical and electrical interlocks, some of them even mandatory, to prevent all these failures. For example, the earthing switch cannot be switched on while the breaker is inserted. But nevertheless, the earthing switch is usually built in a way that it can withstand that amount of electrical, thermal and mechanical stress in case all interlocks go wrong. And here you can see how impressive such duties can be. The low voltage box, as the name suggests, is a box mounted on the switchgear and fully uncoupled from the high voltage. In this box, we install devices that are used to monitor the condition of a feeder or of an incomer. We may be able to visualize if the earthing switch is connected or not, if there is a faulty condition, we may be able to operate some components electrically, etc., etc. An utmost important device is also installed here, the device that protects the consumer. It's called protection relay, and it's used to decide whether the circuit breaker shall trip, meaning open the contacts, or be kept on. The protection relay is able to do a huge amount of other things beyond its main function. It's almost like a small computer which can receive many inputs and make calculations and also send output signals to other components and systems. There are thousands of different devices that can be connected in a low voltage box, from temperature sensors to lamps, switches and transducers in all shapes, characteristics and colors. This is a highly customizable compartment that is designed to fit exactly the needs of each customer. Let us now have a closer look at some of the components used and what are the differences between them. We begin by comparing the specifications of a circuit breaker at home versus those in medium voltage networks. At home, a typical setup might include a circuit breaker with a rated voltage of 230 volts and a rated current of 10 amps, possessing a switch capability of 6000 amps. This configuration ensures protection against most common faults and prevents potential damage from short circuits, typically far exceeding normal operation conditions, as said before. On the other hand, in medium voltage networks, an outgoing panel may feed the equivalent to 10 or 20,000 homes. The amount of energy is much higher, and so are the demands to the circuit breaker on that level. A typical circuit breaker on a rated voltage of 24,000 volts has a rated current of 2000 amps and a switch capability of 25,000 amps. This specification highlights the robust requirements needed to handle not only the higher operation loads, but also the much more severe fault conditions in high voltage networks. So why are circuit breakers that crucial? In order to assure that current flows, they must handle everything in every possible conditions, from normal duty to inductive or capacitive currents and full short circuit currents when faulty conditions occur. Their ability to make or break connections under every possible fault conditions, be it an earth fault, phase opposition, etc., is crucial for maintaining system integrity and safety. Let's move a bit deeper and see how a vacuum circuit breaker, which is by far the most commonly type of breaker used nowadays, is built. Despite several designs from different manufacturers, the basic functions and components are usually consistent. They all have an operating mechanism. This is crucial for open and close operations of the breaker. It controls the movement of the other components, ensuring timely and secure operation, and it's essential for system protection and fault recovery. Post insulators might be used or not, but the mechanism must be somehow insulated from the earthing potential. Any conductive path from the live parts to the earth's metal work must be prevented. The insulators are used not only to withstand that high electrical stress, but must also withstand the strong mechanical forces acting on the breaker, which have the same nature as the forces we discussed before that act on the main busbar. High-quality insulators with a long lifetime are therefore a must. The connecting rod facilitates the mechanical connection between the operating mechanism and the switching element. It transmits the forces necessary to open or close the electrical contacts inside the vacuum interrupter. The heat sink parts in a vacuum circuit breaker assist in dissipating the heat generated by the resistance of the copper to the flow of the electrical current, which is particularly high on the touching contacts of the breaker. This is because no bolts are used, but rather only the force provided by the operating mechanism. The electrical terminals are the points where the circuit breaker connects to the electrical circuit. They need to be robust enough to handle high currents and ensure a low resistant connection. They must also be positioned in such a way that the connection to the switchgear can be done, which is not always an easy task because all switchgears are differently built. Then we come to the place where the magic happens, the vacuum interrupter. This is the core component where the actual circuit breaking occurs. It contains the contact within vacuum. The vacuum eliminates the need for harmful arc-quenching materials, allows for the interruption of arcs with minimal contact erosion and without significant energy waste, and it keeps the contact surfaces permanently clean. In Siemens, our vacuum tubes are maintenance-free and closed for life. Voltage is more or less the variation of electrical field. It's a kind of strength between two poles, and the bigger it gets, the higher the tension between those two poles. To put this in a practical context, think of voltage similar to water pressure within a tube, a force exerted and contained. In this analogy, when the pressure or voltage exceeds a certain threshold, it results in a rupture or a discharge, much like a storm forming lightning when atmospherical electrical charges accumulate excessively. Consider your home's electricity plug, where air serves as the insulating medium between two electrical poles, comparable to a tube's wall resisting to high internal pressure. Here, visualize a nail pressing against the wall of our tube. It's a representation of how an increasing force or voltage can eventually lead to a breakthrough despite the wall's resistance. When the wall's resistance is on the limit, a very small force can be enough for a quick and very energy-loaded rupture on the system. So what are the nails on electrical discharges? Understanding electrical discharges requires insights in two key factors: the spacing between potential charges and the medium occupying that space. With increasing voltage, the necessary spatial separation to prevent a discharge likewise increases. Likewise, when keeping the voltage level, decreasing the distance between the poles increases the danger of rupture. This is what would happen if one would bring both poles closer and closer. This happens sometimes accidentally when someone inserts a metallic object and connects both sides of the plug, or when a faulty cable, short-circuited, is used. The distance between the poles is not enough to withstand the electrical stress. What about the medium? Though vacuum is commonly used, alternatives include pressurized and non-pressurized SF6, sulfur hexafluoride, and oil. As depicted in our comparison, different insulating mediums impact how voltage and distance interplay. The property of each medium determines how much voltage can be applied before a discharge is risked. For example, pressurized SF6 significantly enhances this threshold, followed by vacuum, which explains their superiority as quenching mediums. The different mediums have advantages and disadvantages. SF6 is an excellent insulator. It has a very high dielectric strength. On the other hand, it's a potent greenhouse gas, and it requires careful handling due to its potential environmental impact. Oil is also quite a good insulator, and it's readily available. Its disadvantages are the difficult handling, the potential for leaks and contamination, and the risk of fire. Air at very low pressure, called vacuum, is abundant and inexpensive. It has no environmental impact, and it's very effective at higher voltage. The challenge is that vacuum is technically demanding, and maintaining the ideal vacuum conditions is potentially expensive. So here you see a cutout of a vacuum tube. The terminal disc is a metal plate or disc that is connected to the external electrical circuit. It acts as the entry and exit point for the electric current within the vacuum tube. Terminal discs conduct the high currents and are connected to the fixed or movable contacts inside the breaker. The insulator is typically made of ceramics. It supports the whole vacuum tube and isolates electrically the internal parts of the vacuum tube from each other and from the external casing. They prevent current from leaking through anything other than the designated path between the contacts. The arcing chamber, here made of copper, encases the place where an electric arm forms when the contacts within the breaker separate or come together. The copper provides excellent conductivity and helps dissipate the heat generated by the arc. This is essential for extinguishing the arc quickly and prevent damage to the system. The fixed contact is a static, unmovable contact that is connected to one of the terminal discs. When the breaker is closed, it creates an electrical connection by touching the movable contact. In an open state, it is separated from the movable contact, interrupting the flow of the current. The movable contact moves to make or break the electrical connection with the fixed contact. When the breaker operates, the movable contact pulls away from the fixed contact to interrupt the current and creates an arc in the arcing chamber that is quickly extinguished in a vacuum. Its design is conceived so that the discharge takes place in a smooth way, allowing that the arc doesn't concentrate in one single point, and so not causing damage by melting or overheating the contacts nor components around them. The metal bellow allows the movable contact to move while it maintains the pressure and keeps the vacuum integrity inside the tube. Like the insulator, it must be able to withstand the pressure difference between the normal pressure outside and the very low pressure inside the tube. And finally, the operating and connecting bolt is a conductive bolt that is used to operate the movable contact. It connects the movable contact to the operating mechanism of the vacuum circuit breaker. When the operating mechanism is triggered, the connecting bolt either pulls the movable contact away from or pushes it towards the fixed contact to open or close the electrical circuit. When the breaker is signaled to operate, either to interrupt current or to close the circuit and allow current to flow, a force which was stored in the breaker's spring is transmitted through the rod connected and applied to this bolt, which very quickly moves the movable contact. The precise movement and control of this operating mechanism and bolts are critical as they determine the functionality of the vacuum circuit breaker, ensuring that it responds correctly and safely to operational commands. We're diving more and more deeply into what happens on that magic moment of cutting the energy. Now we get as close as it gets. We will now see what happens on the moment that the electrical connection is interrupted. If we cut the cable of a running motor, we would see a sparkle, an arc. We don't do that because the consequence would be an arc, and that can be dangerous. Instead, we use a switch so that the arc takes place in a controlled and safe environment. That arc can go from invisible to a huge lightning strike, potentially harming people and damaging equipment if not properly managed. So it's nothing to play around with. The arc gets harder to control as higher voltage and more energy are available to feed it. The art of interrupting and connecting the energy, which is, as you will remember, the main function of the switchgear, is to make that in a smooth way that doesn't cause any harm. But there is no known way of doing that without a discharge taking place, particularly when high amounts of energy are involved. But don't underestimate the sparkle also with lower amounts of energy. Also inside those little switches at your apartment, sparkles and cooling down takes place. Therefore, because the sparkle can be avoided, we need to get it under control. 3 of the main challenges are to keep the arc in a confined area, to limit the arc's time, and to cool it down. This is exactly what happens inside the vacuum tube. We distinguish between 2 types of arc due to their behavior during current flow: diffuse arcs and constricted arcs. The main difference is that the way the arc is controlled and used for different magnitudes of energy involved. The diffuse arc is for high energy applications, while the constricted arc is typically used for smaller currents. Therefore, the contact systems for both arcs are differently conceived. They have different geometries. The flat contact works with diffuse arc, while pot and spiral contact systems are used for constricted arcs. The science of the vacuum interrupter design is to ensure almost ideal connection, low resistance, while being connected, and proper control of the arc and ensuring repeatedly operation over 10,000s of operations. The biggest challenge is to manage the extremely hot arc in a way that it doesn't melt the contact surface during operation. Siemens has decades of experience with various designs. Let's have a look at 3 main differences between these 2 types of arcs. A diffuse arc is characterized by its spread-out nature over a larger area. It occurs due to the design of the contact inside the vacuum housing, allowing even the highest energy currents to split up and evenly distribute across the whole contact surface. The design of pot and spiral contacts keeps the arc in a constricted mode and let it rotate at the rim of the contact. It is used for smaller currents and applications with lower energy and allows even more compact designs of a vacuum interrupter. By designing the vacuum interrupter chamber and using the principles of magnetic fields, in both cases, The control of the arc and its movement prevents any hot spot or melting of the contacts, ultimately leading to the arc's extinction at the current zero crossing. Managing such design and the characteristics of the arc is crucial for the effective and safe interruption of the current flow and for ensuring an extremely long life service. Now that we understood how a circuit breaker works, it's easier to understand some different devices by comparing them to the circuit breaker. Let's firstly see the contactor. Its operating principles are very similar to those of a circuit breaker. The main difference is that, unlike circuit breakers, contactors are not meant to interrupt fault currents. Their main purpose is to switch on and off under normal operating conditions. Another big difference is that they are usually conceived to perform a much larger number of operations than a circuit breaker. Whereas a circuit breaker is built to perform something like 30,000 operations, some contactors can perform up to 3 million operation cycles. Of course, the event of a short circuit current occurring must also be protected, even when using contactors, and this is why these devices must be protected by an upper circuit breaker or, more frequently, are used in combination with fuses, which are then used to break the high short circuit currents. Another type of device is the switch. The switch can make or break a circuit while a defined operating current is being passed through it. Essentially, it is designed to interrupt the current flow in a system, but it is not intended to interrupt short circuit currents like a circuit breaker does. It can switch into a short circuit, but it can't open it. In that regard, it is similar to a contactor, but it's a much easier device. It can deal with higher currents than a contactor, but it cannot switch nearly as often as a contactor. Its lifetime is much more shorter. There are mainly two types of switches. The hard gas switches, which use a hard gas, such as air or nitrogen under pressure, and the SF6 switches. Choosing between SF6 and hard gas switches involve balancing environmental concerns with performance, operational and cost factors. The primary function of a switch is to de-energize a section of an electrical line or a piece of equipment to allow for a safe maintenance or servicing. It is used instead of a circuit breaker in situations where there is either minimal or no requirement for fault protection, and where just a simple means to disconnect power is sufficient. This includes systems where another form of protection, such as fuses, is already handling overcurrent protection, or where system protection is not the primary concern. A good comparison is your light switch at home. A switch does approximately the same. It simply switches on and off. If there is a short circuit, there is an upstream device that safely cuts the energy. So when would you select a switch instead of a circuit breaker? When a protective device for failure exists upstream, when it must be easy, cheap and small, when switching can be done manually. In sum, when there is no need for complex functioning and insulating the systems should be done quickly. A typical use is isolating a line or a transformer for maintenance purposes. And now to the disconnector. A disconnector, also known as isolator switch, is an electrical device designed to physically separate electrical circuits, ensuring no current flows through the section being serviced or inspected. It is primarily used for safety purposes, providing a visible gap in the circuit to protect operators during maintenance or when modifications to the electrical system are needed. A household plug can be considered a form of disconnector, as plugging in or unplugging a device physically connects or disconnects it from the electrical supply. I bet you never saw your plug as a device as such, but it is, and it's in fact a very important one. The differences for the medium voltage are, of course, the higher voltage that it can withstand and the higher safety features, such as lockout capabilities to prevent accidental re-energization. So basically, this device fulfills two tasks. It creates a safe insulation and it provides a visible break, allowing the operator to confirm visually that the circuit is de-energized. This is very often required by standards and regulations for safety purposes. A disconnector can't do breaking of any kind of load and also no fault protection. It is used to safely isolate sections during maintenance or upgrade, or to disconnect a segment of a distribution system for an inspection or a repair. And now another device, the switch disconnector. It combines the properties of a disconnector with the ability to switch a circuit under load, meaning under normal operation conditions. Similar to the switch, the disconnector and the contactor, it also cannot break short-circuit currents. The distinguishing characteristics of this device is its capability of withstanding the transient voltage, and that is exactly when it's used instead of a switch, when that capability is needed. And here, better than 1000 words, a short overview of the differences and common things on these three devices. As you see in the right column, none of them can break a short-circuit current. When we need that, we must use a circuit breaker. The switch disconnector is almost the sum of the switch and the disconnector, and that's maybe why we call it switch disconnector. And now the fuses. We already mentioned them before, as they are used in combination with other devices, usually to perform the task of protecting from short-circuit currents. A fuse is a simple yet effective safety device used to protect electrical circuits from overload or short circuits. It has the disadvantage that it's a one-time device. Once it performs its function, its life ends, and it needs to be replaced. The fuse consists of a metal wire or filament that melts when a current above a defined limit flows through it. When it melts, it breaks the circuit. The metal wire has usually some shapes that narrow the strip and are engineered to break at the desired currents and time. The wire is winded on a ceramic star with quartz sand, which is used as a quenching medium that melts into glass when the arc forms, which helps to isolate it. Optionally, some fuses are provided with a strike pin that visually shows that the fuse is no longer usable. That pin is usually also connected to a contact that warns that the fuse has tripped and must be replaced, or to initiate further actions such as activating an alarm, isolating the faulted circuit, or even switching to a backup power source. The whole system is encased in another tube, usually made of ceramic or other insulating material. It must be able to withstand the high temperature and pressure during a fault. Fuses have been widely used in residential electrical systems around the world. In many countries, especially those with an older electrical infrastructures, fuses are still common. Despite the widespread adoption of circuit breakers, fuses can still be advantageous in certain scenarios. Fuses are generally cheaper than circuit breakers, making them a cost-effective choice for single-use protections or in applications where cost is a primary concern. Fuses can react to overcurrent faster than many circuit breakers, providing better protections for certain types of equipment. Their simplicity, with almost or no moving parts nor complex mechanisms, can be an advantage in environments where additional features of circuit breakers are not needed. And finally, the last two components, the current and voltage transformers. They have the task to transform high currents and voltages into small values, which are used for measuring and protection purposes. Transformers provide a scaled-down replica of the voltage or current in the power system, keeping the phase angle approximately the same, which is crucial for certain measurements and protection schemes. These components provide a way of safely observing voltage and current without interfacing directly with the high currents and voltage involved. There are several types of devices that can perform this task. The most common ones are the block-type transformers. You will probably remember them from the cutout drawing of a panel that we saw in the beginning. Let's start with those, and after I will show you also the more modern called low-power instrument transformers. Here is a block current transformer, shortly called CT, standing for current transformer. The current flows through the primary conductor. Usually 3 CTs are used in one panel, one per phase, depending on the protection functions required. The CT is connected to the line carrying the high current that needs to be measured or monitored. It's not more than a U-shaped conductor inside a cast resin housing, which is held by a bottom plate. Around the primary conductor, toroidal cores are fitted. Multiple cores can be used for separate functions such as measurement, protection, and metering, each tailored to specific accuracy and performance requirements. The number of cores varies depending on the application, but typically ranges from 1 to 3 in most designs. The core, typically made from laminated silicon steel, provides a low resistance path for the magnetic flux generated in the transformer. The current signal of each core is wired to the secondary terminals. From there, they are wired to the low voltage box through the cable bushing, and they are connected to the relevant devices that analyze the signal. Because the block CT can't be opened, its characteristics are written on a rating plate placed on its outside. This component provides vital information about the transformer, such as its current and voltage ratings, number of cores, frequency, and other manufacturer details. It helps in ensuring the correct application and management of a transformer throughout its life cycle. The core of a block CT is equivalent to a transformer short circuit on the secondary side. Sometimes cores are designed to measure more than one range of primary current, to allow for adjustment or calibration, or to accommodate different primary current levels. This feature enables one current transformer to be used for multiple applications or in situations where the primary current may vary over time. Internally, this might involve selectable taps on the winding, allowing the ratio of primary to secondary current to be adjusted. And now let's have a look at the block voltage transformer, also shortly called VT, standing for voltage transformer, or PT for potential transformer. Also here, usually 3 are used in one panel, 1 per phase, but not always. Similar to the CTs, it all depends on the design of the protection system. Let's break down its components. The primary terminal is connected directly to the high voltage. Single-pole VTs have only one primary terminal. The secondary terminals are connected to the measurement or protective devices and provide a scaled-down version of the voltage in the primary circuit. The secondary can have multiple terminals depending on the requirements for connection and the provision for different measurement ranges or for redundancy in measurement. The primary winding is designed to handle the high voltage from the power system and typically consists of a larger number of turns of wire. This component is crucial for the step-down of voltage. In single-pole VTs, the primary winding is connected across just one phase and the ground or neutral, in contrast to multi-pole VTs, which can handle multiple phases. The secondary winding serves to step down the high primary voltage seen on the primary winding. The number of turns and wire cross-section are carefully calculated to achieve the desired voltage transformation ratio. The winding is designed to withstand the mechanical and thermal stresses of the operating environment. Similar to the tapping of CTs, it's also possible to incorporate taps for adjusting the voltage output as needed. The transformer core is usually made from high-grade, grain-oriented silicon steel and is responsible for focusing the magnetic field generated by the primary winding, allowing efficient transfer of energy to the secondary winding. The core's design and material are vital for achieving high accuracy and minimal energy losses. For insulation and protection against environmental conditions, the winding and the transformer core are embedded in cast resin, using the same principle as we saw for CTs. This material provides excellent dielectric strength to withstanding high voltages, while also protecting the internal components from moisture, dirt, and other contaminants. And finally, the earthing terminal. The earthing terminal provides a crucial safety feature. It ensures that the transformer and the connected secondary circuitry have a reference point at ground potential, helping protect against electrical shock and reduce electromagnetic interference. Besides the single-pole VTs, there are also two-pole VTs designed for specific applications, mainly where a connection across two phases is needed. These are useful in systems where a direct neutral earth connection is not available, or in certain types of metering or protection schemes that require the measurement of voltage that span across two phases instead of phase-to-neutral voltage. In essence, two-pole VTs extend the flexibility and applicability of voltage transformers to a broader range of electrical system configurations and requirements. There are other types of transformers beyond the traditional block-type transformers, the so-called low-power instrument transformers, or shortly LPITs. As our systems and technologies evolve, so too do the tools we use to monitor and protect them. LPITs are a modern and increasingly common alternative to the traditional instrument transformers, combining the functionalities of high voltage and current transformers, but with several distinct advantages. I have listed 7 advantages. First, LPITs are compact and efficient, providing both voltage and current measurements in a single device. You will remember when we talked about the block transformers that we need separate devices for voltage and for current. If you consider that transformers are usually needed in the 3 phases, we need only 3 small LPTIs compared to the 6 big block transformers. The LPTIs consist of a Rogowski coil, which is an air coil, and doesn't require a ferromagnetic core for the current measurement. Its output in voltage is in the range of millivolts. Second advantage, LPITs are safer than the classic block transformers because they reduce the risk of open circuit condition in the secondary winding. One major hazard during the commissioning and operation of protective devices is the handling of the secondary circuits of the current and voltage transformers. Correct winding and handling must always be ensured for both to avoid accidents. However, a special property of LPIT technology is the low output power and the small secondary voltage of the sensor. This range from millivolts to a few volts. Thus, the danger for executing personnel is significantly lower compared to the conventional transformers. These involve many cables and terminals and are inherently prone to human error. In LPTIs, a single cable plugged in the relay directly from the LPITs reduces human interaction and certainly leads to a decreased risk of malfunction. Third advantage, LPTIs are significantly smaller and lighter, which makes their installation and maintenance easier and more cost-effectively, especially in constrained spaces. Fourth, LPITs have digital outputs and are therefore inherently suitable for integration with modern smart grid technologies, offering advanced diagnostics and communication capabilities. Fifth, LPITs are reliable. The sensors are immune to grid disturbances such as ferroresonance phenomena. They are linear over the whole measuring range, even up to the rated shorted circuit fault currents. This goes alongside with a higher accuracy in measurement when compared to the classic block transformers. Sixth, LPITs are flexible. Due to a single design with a wide dynamic range covering almost all possible requirements, LPITs allow for easy adaptation to the changes in the network, as for example changes in the feeder current with the allowed range of the functional unit, even at the final stage of the manufacturing process or at customer sites. If you remember, one of the features of block transformers was a tapping, which consumes more material to achieve this flexibility. And final, seventh, LPTIs are environmental friendly. They support making switchgear more sustainable, not only during the manufacturing phase, but also during their lifetime because they consume much less materials like iron and copper. On the other hand, they also have lower power consumption and minimal electromagnetic radiation. Therefore, they help to reduce energy consumptions and CO2 emissions, which means lower purchasing and operating costs for customers. Thank you for your attention and see you on the next sections.